In this unit, we will introduce hypothesis tests and give an overview of their use, their interpretation, in particular the difference between proof and inference, and give a step-by-step method to carrying them out. Suppose I have a theory that male actuaries are 6 foot tall on average, or 182.88 centimeters for those who prefer metric. We call this statement a hypothesis, and as actuaries we will want to test this hypothesis to see if it reflects reality. This, unsurprisingly, is called a hypothesis test. Our original default hypothesis is called the null hypothesis and is denoted by H subscript 0. So in this case, our null hypothesis is that mu, the true population mean height of male actuaries, is 182.88 centimeters. Well, suppose we're wrong. What will we then say about the mean height? Well, if we reject our null hypothesis, then we will go with what's called the alternate hypothesis, which is denoted by H subscript 1. Now in this particular case, we have nothing to suggest that the mean height of actuaries would just be less than this 6 foot or greater than this 6 foot, and so our alternate hypothesis will just be that it's not 182.88 centimeters. So how do we test this? Well, we'll collect some sample data and examine it to see if it's consistent with our hypothesis. So suppose we collect the heights of 10 male actuaries, which are given here, and look at their sample mean, which is 180.33. Well, we can see it's a little bit different to our null hypothesis of 182.88. The question is it so different as to be considered significantly different? Well, if we make an assumption that the heights of male actuaries are normally distributed, then from a previous unit, you'll recall the following result. X bar minus mu over S over root n has a t distribution with n minus 1 degrees of freedom. Well, in this particular case, our n is 10, and so we'll have a t9 distribution. And so by calculating the value of this formula, we can see how far we are through the t9 distribution, which will help tell us whether our sample data is consistent with our null hypothesis. Now, if we're in either of the extreme ends of this distribution, then we will conclude that our sample mean is so different from our hypothesis mean that it is significantly different. That is, it's very unlikely to be this different due to chance. The question is, how different is significantly different? Well, the industry standard is to take the extreme 5% of results. Well, we need to split that 5% between the two sides, so that'll be 2.5% either side. Looking up the t-distribution in the tables, we can find the values of the distribution on the edge of this shaded region. These are minus 2.262 and plus 2.262. These values are called the critical values, and the shaded region is called the critical region. A value of our formula more extreme than these critical values would indicate that our sample mean is significantly different from our null hypothesis mean. Well, let's have a look. Substituting in our values, our x bar is 180.33, and we'll take away our null hypothesis mu of 182.88. We then divide this by the sample standard deviation, which can be shown to be 5.2785, over root 10. Well, this gives us a value of minus 1.528. So looking at this distribution, we can see that our sample mean of 180.33, though different from our null hypothesis mean of 182.88, isn't different enough to be counted as significantly different. And so it's reasonable to conclude that our null hypothesis is correct. The question is, have we proved that the mean height of male actuaries is 182.88? Well, the short answer is no. What we have shown is that our hypothesis seems reasonable based on our sample results and assumption of a normality, but we haven't proved it. It's what's called statistical inference. We have inferred that it is true, though we haven't actually proved it. Unlike pure maths, actuarial science and science in general can't prove results. It just shows that the theories are reasonable given the data, but these must always be held lightly as further information may come to light which would invalidate our theories. Similarly, if the sample mean was so different as to be in one of the extreme shaded regions, called the critical regions, would that have meant we have disproved our null hypothesis? Again, the answer is no. All we have done is infer that it is unlikely, given our sample data and our normality assumption, because there's still a chance that it may actually be true. For example, I might have picked a sample which happened to contain several actuaries who were basketball players and therefore very tall. This would give a large sample mean, which would lead me to reject the null hypothesis, even if it were true. In a later unit, we'll look more closely at the errors that can be made under a hypothesis test. But for now, you just need to be aware of the difference between inference and proof, and that any actuarial models we come up with to predict the future are only reasonable given the data and assumptions that we've made. History is littered with examples of those who have forgotten that our models are based on inference rather than proof. For example, the company Standard Life made an assumption that interest rates would never fall below 4%, because they hadn't, and so put in a guarantee into their annuities. When they did, the company went bankrupt. Also, the firm Long-Term Capital Management based the pricing of options on the Black-Scholes model, which assumed normality of log returns, and when things became different, that company also went bankrupt. So beware. Well, let's formally go through the method which makes up a hypothesis test. Step 1, we will have to state our hypotheses. Our null hypothesis, denoted by H0, is what we believe things to be, and must always be an equals. For example, we had that our mean height of actuaries was equal to 182.88. Our alternate hypothesis, denoted by H1, is what must be the case if the null hypothesis does not hold, and that can be a greater than, a less than, or a not equals. In our previous example, we said it was not equal to 182.88. Step 2, we need to choose a formula. This is called a statistic. Now in our example, we wanted to test the population mean mu, and so we needed to choose a formula which had mu in it, which was this t result. Similarly, if we were carrying out a test on the population variance, sigma squared, we'd need to choose a formula that had sigma squared in it. Step 3, we need to obtain our critical values. These are the values which bound our critical or rejection regions. In order to do this, we need to first decide whether the test is one- or two-sided, and we do this by looking at the alternate hypothesis. In our example, our alternate hypothesis was mu is not equal to 182.88, and so we would have rejected the null hypothesis had it been too big or too small, and this is a two-sided test. Next, we need to attain the level of the test. This is the size of the critical or rejection regions, i.e. how different a result has to be in order to be counted significantly different. The industry standard is 5%. So in our particular example, we split that 5% over the two critical regions, so we had 2.5% in either region. And the values indicated by the blue arrows are our critical values, the values which bound our critical regions. If our alternate hypothesis was a less than, then we have a one-sided test, and we would only reject the null hypothesis for small values of our statistic. And so our critical region is only at the lower end of the distribution, and the full 5% would go there. Again, the blue arrow indicates the critical value. Finally, if our alternate hypothesis was greater than, again we have a one-sided test, and we would only reject the null hypothesis for large values. And so our critical region is at the upper end of the distribution, and the full 5% goes there. Again, the blue arrow indicates the critical value. So now we have our critical values, we're ready to proceed to step 4, which is to calculate the value of our statistic. So on our particular example, we substitute in our sample mean of 180.33 and our null hypothesis mean of 182.88, along with our sample standard deviation and sample size. And this gave us a value of -1.528. Our final step is we compare this statistic to our critical values. So in our particular example, we saw that the value of our statistic wasn't extreme enough for us to reject the null hypothesis. In general, we will say either there is insufficient or sufficient evidence to reject the null hypothesis at the blah 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 % level. Usually this is the 5% level, as that's the industry standard. Well, let's talk about this wording. In our particular case, we would say there is insufficient evidence to reject H0. What we're saying is, based on our sample, it seems reasonable, but we're not saying it's outright true, because it may be, with a different sample, that we discover things are slightly different. Furthermore, we always talk about rejecting the null hypothesis, rather than accepting, because to accept it is to say that it's definitely true, and that would imply that we're proving it. And the % level is important, because this tells us how sure we can be. Where the level is 5%, we're basically saying that we're 95% sure that our result is correct, just like a 95% confidence level, or if you like, there's a 5% chance that we've bodged it. We'll look at this in more detail in a later unit. And the final line of our conclusion would be where we say it is reasonable to assume that whatever we conclude. So in our particular case, it was reasonable to assume that mu was 182.88 because we didn't have any evidence otherwise. So we assumed the null hypothesis. Note we say the word assumption because it is an assumption, as we haven't proved that it is true. Similarly, if we rejected the null hypothesis, we would have said it would be reasonable to assume that it's not 182.88 because our sample data is so extreme as to make us think that that would be unlikely. These are the 5 steps that we'll be using in all the following units when carrying out a hypothesis test. Here's a summary of what we covered in this unit.